Hello, welcome to the playlist of videos on probability distributions. I am Hemukumar Kasala, and in this video I wish to explain what a random variable is and how does it specialize as against a variable. Two forms of random variables, namely discrete and continuous, and finally an introduction to the probability distributions of discrete and continuous random variables. Let's get into the video. Let's take the case of a popular store that sells a wide range of household items in a locality. Let's conduct a chance experiment wherein a customer exiting the shop is chosen randomly, one at a time, and the number of items that the customer has purchased is noted as the outcome of the chance experiment. Let's repeat the chance experiment and repeat it a number of times such that the sample space is populated with the outcomes of many rounds of this chance experiment. While the number of items that a customer can buy is a variable, let's represent that as V. The numbers populated in the sample space are random values within the possible range for V each time the chance experiment is executed. The numerical variable X that represent the sample space is hence a random variable. Let's consider the same store again, and this time conduct a chance experiment wherein a customer exiting the shop is chosen randomly, one at a time, and the amount of time the customer has spent standing in the queue in minutes is noted as the outcome of the chance experiment. Let's repeat the chance experiment and repeat it a number of times such that the sample space is populated with the outcomes of many rounds of this chance experiment. While the amount of time that a customer waits in the queue is a variable V, the numbers populated in the sample space are random values within the possible range for V each time the chance experiment is executed. Note that the outcomes in the sample space are continuous values in this case, whereas the ones generated in the previous case were discrete values. By definition, random variable is a numerical variable whose value is decided by the outcome of a chance experiment. Random variable is a discrete random variable when the outcomes in the sample space are discrete values, and is a continuous random variable when the outcomes in the sample space are continuous values. While all possible values for a discrete random variable is represented by a collection of isolated points on a number line, all possible values for a continuous random variable is represented by an interval on the number line. Outcomes of a chance experiment as such need not always be numerals. However, numerical aspect is associated with outcomes in order to arrive at some targeted analytics. Let's understand this with an example. Let's take the case of a national park that is vast and provides a number of places for visitors and trekkers to explore. It operates bus services to help visitors explore the extensive area. There are two different bus routes, one blue and the other green. Each one of these services operate their respective buses according to a predetermined schedule. However, buses cannot stick to their timetable strictly, and often there are delays. Let the chance experiment conducted in this case records the colors of three successive buses arriving at one carefully chosen bus stop in the park. Sample space consisting of the possible outcomes will look like this. Note the outcomes in the sample space are not numerals in this case. Assume the study is aimed at examining the probability of two buses belonging to the same route arriving in a succession. That is, the two buses of the same color arrive in sequence in a given trial. These are the possible outcomes that will quantify that probability. Now arises the need to transform the outcomes in the sample space to appropriate values or numerals so that the aim of the study is achieved. Assigning some probabilities to events B and G, for example, assuming that the probability of the next bus arriving at the given bus stop is a blue bus, that is, probability of B equals 0.4, and The probability that the next bus arriving at the given bus stop is a green bus, that is, probability of G equals 0.6. The probabilities associated with each of the outcomes in the sample space can be arrived by applying the multiplication rule. For example, probability of BGB equals probability of B multiplied by probability of G multiplied by probability of B, which equals 0.096, and probability of GGB equals probability of G multiplied by probability of G multiplied by probability of B, which equals 0.144. This association of numerical values enable the evaluation of the result for the current experiment. That is, what is the probability that two buses belonging to the same route arrive in a sequence? The answer is the sum of the probabilities of those outcomes seen inside the yellow circle, which equals 0.76. Thus, we see the need to associate numerical values with outcomes, even where it is not the case, to arrive at the analytics. Note, discrete random variables does not necessarily mean finite set of values, can be infinite as well. Let's see this case via this example. Let's consider a tennis match where A and B play against each other. The match is regarded as concluded when any one of the two, A or B, wins two consecutive sets successively. Let the chance experiment conducted in this case records the sequence of winners of each set on the completion of the match. The sample space will populate something like this as the chance experiment gets repeated. As one can see, the number of sets to finish a match can be any number starting from 2 onwards, extending to infinite number of sets. Thus, discrete random variable does not always mean a finite set. Probability distributions. In the chance experiment where the number of items bought by each customer and their waiting times were recorded, one may have the following questions. What's the probability that customer buys exactly 4 items from the store? What's the probability that a customer buys not more than 5 items from the store? What is the probability that a customer waits for more than 3 minutes in the queue? And what's the probability that waiting time for a customer in the queue is between 3 and 5 minutes? And similarly, what's the probability that the blue and the green bus services arrive alternatively in a given trial? And what's the probability that the number of sets does not cross 10 rounds in a given match? In order to answer these questions, one needs a probability distribution of that random variable. Probability distribution describes the long-run behavior of a random variable. We shall discuss how the x and y axes are treated differently for discrete and continuous random variable cases individually later. Let's answer this question first. How to generate the long-run behavior for a random variable? In order to generate the long-run behavior, the chance experiment should be conducted and repeated over a large number of times such that the sample space is populated with the outcomes over this long run. And these values from the sample space constitute the long-run behavior of the random variable. The probability distribution of the random variable is derived from the values out of the sample space that are generated as discussed. The relative frequency of occurrence for each of these values from the sample space are plotted and also captured in a table format or a mathematical expression. The same applies to continuous probability distribution as well, though what is depicted above is the discrete probability distribution. As discussed, probability distribution of a random variable is also captured as a mathematical model or in a table format. And it is this model or table that is used to derive the answers to these questions that we discussed a while ago. Probability distributions for discrete random variables. Definition. Probability distribution of a discrete random variable x provides the probability for each of the possible values of x, where probability equals limiting long-run relative frequency for each value of x. Ways to represent the probability distribution are models in the form of mathematical expression or a formula, or tables, and or histograms. Let's revisit the National Park chance experiment in order to understand the probability distribution for a discrete random variable in detail. Let's tabulate the outcomes from the sample space. Let's start by listing the outcomes in the first column from the sample space, followed by the probabilities for each of those outcomes in the second column. We already discussed how to calculate the probabilities for the outcomes. For example, probability of BGB equals probability of B multiplied by probability of G multiplied by probability of B, which equals 0.4 multiplied by 0.6 multiplied by 0.4, which in turn equals 0.096. And finally, let's add the column that records the number of arrivals of the green bus in each trial. If the number of green buses in a given trial is chosen as the random variable x, then the possible values for x are 0, 1, 2, and 3. And their respective probabilities are probability of x equals 0 equals probability of BBB, which equals 0.064. Probability of x equals 1 equals probability of GBB plus probability of BGB plus probability of BBG, which sums up to 0.288. And probability of x equals 2 equals probability of GGB plus probability of GBG plus probability of BGG, which sums up to 0.432. And probability of x equals 3 equals probability of GGG, which equals 0.216. These discrete probabilities calculated for each of the possible values of x form the probability distribution for the discrete random variable x and captured in the table form as shown below, with the possible values for random variable x listed in the first column and the respective probabilities listed in the second column. The graphical form for the discrete probability distribution in the table is the histogram representation as shown. In a histogram representation, all the possible values for the random variable x are shown on the x-axis, and their respective probabilities are shown using rectangles centered above each of the values for x, with area of the rectangle equal to the respective probability value. Note, it's the area of the rectangle, not the height. Now let's take a look at the kind of questions we discussed for which probability distributions should provide the answers. What's the probability that 2 green buses arrive in a given trial? The answer is probability of x taking the value 2, and that equals 0.432. What's the probability that more than 1 green bus arrive in a given trial? More than 1 green bus means 2 or 3 green buses, and hence the answer is the sum of the probabilities where x takes the value 2 and 3, which sums up to 0.648. What's the probability that not more than 1 green bus arrive in a given trial? Not more than 1 green bus means 0 or 1 green bus, and hence the answer is the sum of the probabilities where x takes the value 0 and 1, which sums up to 0.352. Properties of discrete probability distributions. For each possible value of the random variable x, probability of x is greater than or equal to 0 and less than or equal to 1. That is, the probability associated with each possible value of the random variable x can be 0, 1 or any value between 0 and 1. However, the sum of the probabilities for every possible value of x equals 1. That is, the total probability does not exceed 1, which is nothing but stating the obvious. As x takes the value 0, 1, 2 or 3, probability of 0 plus probability of 1 plus probability of 2 plus probability of 3 should equal 1. Substituting the values 0.064 plus 0.288 plus 0.432 plus 0.216 indeed equals 1. In other words, total value of areas of all the rectangles equals 1. Probability distributions for continuous random variable. Let's consider a random variable x, which is a collection of samples out of a population from a locality whose values are height of the individuals in cm. This histogram represents the probability distribution for the above sample. Assume range encountered for the heights is between 140 and 200 cm. Note the value of x is a real value and its accuracy, in other words, the number of decimal digits to represent the value depends on the measurement system deployed. It can run into many digits deep accordingly. Values of x are clubbed into these following bins. The intervals for the bins are greater than or equal to 140 and less than 150, greater than or equal to 150 and less than 160, and so on until greater than or equal to 190 and less than 200. And the probability corresponding to each of these bins is captured in this histogram. Suppose values of x are clubbed into further narrower bins as in greater than or equal to 140 and less than 145 and greater than or equal to 145 and less than 150 and so on until greater than or equal to 195 and less than 200. Then the histogram shall display narrower rectangles as shown. Assuming the sample set is large enough, the bins can be narrowed further and the rectangles in the histograms get narrower and narrower. And eventually the histogram shall become a smooth curve when the width of the rectangle tends to 0, thus resulting in a continuous probability distribution. Continuous probability distribution results out of cases where the possible values of x typically are infinite but confined to an interval. And importantly, intervals of interest within the range of x cannot be aligned with fixed bin intervals and can vary. And the values of x are in real numbers, not integers. Probability distribution for a continuous variable x is a smooth curve specified mathematically as a function of x, f of x. F of x is also called as the density function. F of x satisfies the following requirements. F of x is greater than or equal to 0 for all values of x. That is, f of x can never be negative. Integral of f of x over the possible range for x equals 1. In other words, the area under the curve f of x equals 1. Probability that x falls in a particular interval x greater than or equal to a and less than or equal to b equals the area under the curve denoted by f of x over the interval a and b. Mathematically, probability of x greater than or equal to a and less than or equal to b equals f of x integrated over the interval a and b. Probability of x greater than or equal to a and less than or equal to b equals probability of x greater than a and less than or equal to b and probability of x greater than or equal to a and less than b and probability of x greater than a and less than b. This is because the probability that x equals a certain value, say a or b, is 0. And that's because the width of the curve above a point a or b is infinitesimally small, in other words 0. Probability that x falls within the interval a and b, that is, probability of x greater than or equal to a and less than or equal to b, where a takes the value 0.25 and b takes the value 0.75, say, equals cumulative area of the probability density function to the left of b, that is, probability of x less than or equal to b, minus cumulative area of the probability density function to the left of a, that is, probability of x less than or equal to a. That brings us to the end of the session on understanding the basics on the probability distributions and random variables. Please share your questions and remarks if any, and I'll try and respond back as soon as possible. Thank you, and see you with the next session on the playlist of videos on probability distributions. Bye until then.